Hello everybody, Nerdiology here, and back to you with another 2020 local section exam video, this time covering questions 49 to 60, which is organic chem. So let's begin. 49 starts off easy, and it says, which molecule is planar? So the key is just Vesper, you draw out the Lewis structures, and that will give you the geometry. So let's begin. So if you draw out CF4, right? So you can go CF4. From there you can see it's tetrahedral. From B, right? This is your Lewis structure. This is COF2's Lewis structures. And here at this moment you can pretty much stop, right? Because you have 3 bonding sites, and that will equal to trigonal planar. So you can cross at A and any other answer choices, and be left with B, right? So yeah, that's 49, pretty easy question. Alright, let's move on to number 50. Which molecule has no unpaired electrons? So there's 2 ways to find if a molecule has unpaired electrons. You can first count its valence electrons, which I'll do for A. So if you count the valence electrons for NO, nitrous oxide, so you get 5 plus 6 equals 11. And then since there's an odd number of valence electrons, it means one of the electrons will be unpaired. So A is off. So if I draw a Lewis structure, you can see this better. So we have the Lewis structure for nitrous oxide is this. You see this? You see this electron? This electron is unpaired. It doesn't have another electron next to it, so you can cross out A. For B, you have to draw a molecular orbital diagram. But if you don't know what those are, I suggest you take a nice read of them. They're not that hard to understand, but let's draw one for you. So we have 2 oxygen atoms, and let's draw their 2p orbitals. Right, so we're going to create a sigma 2p, pi 2p, an anti-bonding pi 2p, and an anti-bonding sigma 2p orbital. And each oxygen atom has 4 2p electrons, and from there you just fill it up. And over here you see there are 2 unpaired electrons in the anti-bonding 2p orbital, so you can cross out B. For C, you cannot find out, so if you do the math, right? If you do the complex map of finding the amount of valence electrons in the molecule, will get 18, right? Because 6 plus 6 plus 6. But then, so you don't know if it has unpaired electrons or not. But oxygen also has an even amount of valence electrons. So we'll leave C off for now. Let's take a look at D. Now D, let's count the valence electrons of the molecule. So you have 7 of chlorine, plus 6 for another oxygen atom, plus 6 for the other oxygen atom, and then you get 19 electrons. And that is an odd number. So you can cross out D, and C, by process of elimination, is your answer. Let's move on to 51. We move on 51, right? So this one isn't too bad of a question. 51. So phosphorus acid is a dipyritic acid in aqueous solution pK1, pK2. So which Lewis structure best represents HPO3 2 minus? So you can easily cross out A and B because the acids doesn't have a peroxide in it. It's pretty unstable. Acids don't usually have like peroxides in them, so we can cross out A and B, right? Let's take a look at C and D. Now, you make a little stumped on this, right? But keep in mind that C basically signals C's answer, and the reason why is that it signals the acid's diprotic, right? Because if you take a look at D, right, where will all the other hydrogens go? they would go to the two oxygens that have the negative charge in D, right? And usually when a proton is connected to an electronegative element like an oxygen, it will have acidic character. So D signals a triprotic acid, whereas the question says phosphorus acid is a diprotic acid. So you can cross out D, right? Because in C, right, because in C, right, if you have phosphorus acid, the two extra hydrogen atoms will be connected to one of the oxygens, and those will be acidic, not the one connected to phosphorus. So that means C is correct. 52 is a nice, good old trick question. So, one Lewis structure of the squared ion C4042- is shown below. Which statement best describes the bond distances of the squared ion? All carbon-carbon bond distances are the same in all carbon-oxygen bond. Yes, that's true. The entire molecule has multiple resonance structures, right? And that means, like, if there's a blend, the real molecule is a blend of those different resonance structures. It doesn't alternate between double and single bonds, right? So A is good. B, there's two distinct, no. That just goes against what I said. C, there's two distinct, no. D, there's three distinct, no. It just goes against what I said, and that means A is the answer. So keep in mind that, like, it's a blend. The molecule is a blend of the different resonance structures. So that means all carbon-carbon bond distances are the same. Moving on. 53. This one's a slightly tricky question, but we'll see. So the bond distance in carbon monoxide is 112.8 pm, while the bond distance in NO is 115 pm. Which is the best explanation for the shorter bond in what do you call it, carbon monoxide? So it says that 52, right? 53. Carbon has a smaller atomic radius than nitrogen. That's wrong. Because if you take a look at the periodic table, right? Nitrogen has one more proton and has a higher nuclear charge than carbon. So then it'll take a greater hold on the valence electrons, just contracting them. Right, so nitrogen is the shorter molecule, the smaller atom. So C's out. Carbon can form up to 4 bonds, while nitrogen can form up to 3 bonds in D. No, I don't think that matters. Carbon is less electronegative than nitrogen. No, that's really irrelevant in this. So what this question is asking you is to interpret molecular orbital diagrams. So I recommend you to draw the molecular orbital diagrams of carbon monoxide and nitrogen monoxide and draw the bond order and find out the bond order from there. Right? So the equation for bond order is, the equation for bond order equals 1/2 bonding electrons minus anti-bonding electrons. So like I said before, learn how to draw the molecular orbital diagrams and then find out. And bond order is inversely proportional to bond distance, and you can find out why A is the answer. So moving on to 54. How many stereoisomers is a square planar complex? Yada yada yada. Okay. Now you think this is like they deal with combinatorics and permutations? No. Also, you think that you have to draw all the possible molecular structures out? No. I'll show you a little trick we can do this to solve this problem. So we're going to list out our key, right? So our A is going to be NH3. our B is going to be bromine, and our C is going to be chlorine, right? So now you're going to group them into parentheses like A, and B, C, right? And this means that these are opposite from each other. So if you have a square, right? A is here and A is here. Now you're going to find as many combinations of these via repetition. So this is one combination, and another one is AB and AC. Those are the only two combinations you can make with this scheme, and the answer is B or 2. Moving on to 55, and we'll get some organic chemistry, sweet old organic chemistry. This one isn't too bad of an organic chemistry, probably if you know your functional groups. So A, does it look like an ester? Yes, it does look like an ester. An ester group, this is an ester group. Oh no, oops. So this is an ester group, right? So you have a carbonyl, then oxygen bonded to one area, then 2 R groups. That's an ester. Now B, you may think it's an ester, right? But it's just a cyclic anhydride. An ester only has one direction, where the anhydride has a carbonyl, both carbonyl groups surrounding an oxygen. So this is a cyclic anhydride group, and you cross at B. C is an alcohol because it's an OH group, and D is just like, I don't know, cyclic ketone or something. So A is our answer. Moving on. A pure substance is found to rotate the plane of plain polarized light. Which compound is it? Okay, what this question means is that which compounds are chiral? Now, for a molecule to be chiral, one of the carbon atoms must bear 4 different groups to it. Now, in a compound that's cyclic, you may realize that sometimes there's not 4 different groups to it, right? You think that there's one cyclic group and one hydrogen and one OH, right? But here that's not the case, so listen to me out. So the answer is D in this case. Here's why. So let me draw the molecule out. Right, so this is your carbon out of increst to check if the molecule is chiral. So we have one group here. There's one implied hydrogen here. Now you gotta check the other groups. So in a cyclic molecule, if you want to check if something's chiral, you gotta look at a point of reference. So our oxygen atoms are going to be a point of reference, and we're going to see if the 2 paths to go to the oxygen are the same, right? So let's begin. So to go to this oxygen atom, you only need 1 carbon, and to go from this way, it takes 3 carbons. So there's 2 different paths to go to this oxygen atom, so they'll count as 2 different groups. So that means D is the answer. Try this to the other molecules, A, B, and C. You won't see there's like a situation like this. So yes. 57. This is a little bit more advanced, I guess, organic. So this is here, what you see is a substitution reaction. More specifically SN2. So that's SN2 reaction or substitution. Right? So what are the 2 components needed for a substitution reaction? So the first thing is you need to have a negatively charged attacking molecule that will, let me show what I mean. So you need a negatively charged molecule, right? or molecule that bears a lone pair or something like that. And that's going to be your nucleophile. And then your electrophile is opposite. Your electrophile is a positive region in a molecule. So the nucleophile will get attracted to the electrophile and will drive out the leaving group. So, okay, so whenever you see a molecule like C3Hi, right, this is gonna be your electrophile. The negative charge goes here, and then the positive charge goes there. And something like sulfur, which bears lone pairs, right, will attack, since it's negative charge, it will attack this molecule, right? And to satisfy the octet, nitrogen leaves. So then when nitrogen leaves, you will get the molecule H3, CH3, CH3. Right? So that means, so essentially what happens is like the nucleophile gets attracted to this positive CH3 group in the CH3I molecule, and this drives out the iodine, and then you get the final molecule, which is B, and that's your answer. Moving on to 58. 58 is a pretty easy problem. So how many distinct compounds have the formula C5H12? Okay, so the first thing when you're counting isomers, you need to find out the double bond equivalency, and it's through this equation. So double bond equivalency means the number of carbon atoms plus 1, number of carbon atoms plus 1 minus H2 minus halogens over 2 plus nitrogens over 2, right? So there is 5 carbon atoms plus 1 over 12 hydrogen atoms divided by 2, and that equals 0. So what you're dealing here is an alkane. So now there's no rings or no double bonds, so we just have to draw them out. So the first isomer, this is just takes practice if you want to find them all. So the first one is this one, the second one is this one, and the third one is this one, right? So that is our answer, and 58 is therefore C. Moving on to 59. Okay, so it says, which compounds reacts the fastest in electrophilic aromatic substitution reactions, such as with Br2 in the presence of FBr3? Okay, so this is something you have to memorize. You have to memorize electron donating groups and electron withdrawing groups, right? So electron donating groups essentially donate electron density to the aromatic ring. And as I said before, like in question 57, when you donate the electrons to the aromatic, it becomes more negative and a stronger nucleophile. So attack the electrophile, that is the reagent, to create an electrophilic aromatic substitution reaction. So we're going to find out which ones are the electron donating groups. Now let's take a look at A. So A, CH3 is an electron donating group, a weak one though. So it donates electrons via hyperconjugation. And hyperconjugation is when a pi bond, not a pi bond, a sigma bond, right? A sigma bond between the carbon atom in the benzene group and the CH3. The carbon atom bonded to the methyl group. The carbon atom in the benzene group bonded to the methyl group. So in hyperconjugation, a sigma bond, right, donates electrons to a p orbital, right? So in this case, there's p orbitals here, p orbitals here, p orbitals here, p orbitals in all of the 6 carbon atoms. This sigma bond donates electrons into here. That is how it is. So this sigma bond over here, when I had trouble saying it donates electrons into this pi bond. So that means you can keep an E, right? NO2. So NO2 group, the nitrogen apparently has a positive formal charge. And since it's a positive formal charge, it will take electrons to compensate for the positiveness by the formal charge. So it will withdraw electrons. So that means the benzene ring is less nucleophilic and will be weaker in electrophilic aromatic substitution. So that means NO2 E withdrawing group. So B is wrong. C. So yes, OH3, the methoxide group, is an electron donating group. Here's what I mean. You may think that oxygen is electron negative, right? You think oxygen is electron negative, but it donates electron density through resonance. Here's what I mean. So this is here, I'm going to draw this benzene group, OH3. So this will donate electron density here. Through resonance, it will make its electron pairs go here, and benzene participates in this resonance structure, donates electron density through to the ring. So here's an example for resonance structure. A negative charge here, and then yeah. So this is why C, or the methoxy group, is a electron donating structure, and it is much stronger than A because resonance is a stronger factor than hyperconjugation. So that means you can cross that A. And Br is electron withdrawing, so is deactivating group. So C is the correct answer. Let's move on to 60. Which statement about unsaturated fats is not correct? Unsaturated fats, yes, this is just your honors biology course concept. So yeah, so unsaturated fats contain carbon-carbon double bonds. Yes, they do. So that means you cross out A. Unsaturated fats generally have higher melting point than saturated. No. And unsaturated fats have a kink, right? Have this certain kink. So we have a certain kink to one of the fatty acids. And that kink does not make the molecules orderly. So that means it will have a lower melting point. So that means B is wrong and therefore correct answer. Let's take a look at all the answer choices. Unsaturated fat can be converted to saturated fats by treatment of H2 in the metal catalyst. Yes, that's true. In the metal catalyst, some of the metal catalysts include palladium, platinum, or nickel. And D, unsaturated fats must contain oxygen. Yes, they do. See, so there's a glycerol group which contains oxygen. The glycerol group contains oxygen. So because of this, you can cross out C and D, and B is our answer. Alright, wasn't too bad. I felt that the organic was a little easier than last year, but this exam overall was harder than last year. It will keep on getting harder. So you must solidify your concepts by reading a general chemistry textbook to make sure that you're confident for next year's exam. Thank you and have a great day.